my kids can look at it. Cool. So finishing going along with 11.3 notes, we're going to look at the extra practice. These problems are asked to find the area of a kite or a rhombus. Turn back in your notes. What's the formula for the area of a kite or a rhombus? Look back.
Oh.
Kite rhombus, bottom of the first page. 1/2 times D1 times D2, and we talked about how the D1 and D2 are considered to be the diagonals. So the first thing that I want you guys to do is grab, now these 10s, I'm going to tell you right here, go along with this diagonal. Take one of your colored pencils and highlight it. And then let's bring that whole measure out here, just like they did in the drawing. So you've got one of your colors right now that we're just trying to show this diagonal for.
Isn't it 20?
And that was my next question, Sean, is how long is that diagonal? So I'm going to pull that outside and put together the 10 and the 10.
Okay, the side is 14.
And then there you go. Sean's moving ahead. That's what I'm hoping for. So then this length right here, the 7 and 7, is going to be the other diagonal, and we'll pull that out as 14. And then Alyssa had given us the formula over here. So I'm just going to pick up my pencil and fill in the D1, D2, the diagonal length, 1/2 times 14 times 20. So just trying to like make these notes super useful so you have examples to look back on when you work on some of this stuff by yourself. Ashley, you guys got 140, that makes sense. 1/2 of 14 is 7. 7 times 120, I'm right there with you. Now I'm going to drop in the inches squared because really this was 14 inches times 20 inches. Inches times inches is going to leave us with inches squared. Am I keeping you awake? All right, now let's go over here. How about this diagonal length for the kite here? How long is it? This is going to be 4 centimeters. Now, which one is it? It's going to be 8. It's going to be 8. Stop arguing, you guys. You're doing fine, Sean. Oh, why did I write centimeters? That one's an inch. Or why did I write inches? It's in centimeters. So then I know that the diagonals are 4 and 18. I'm sorry, 8. Jeez Louise, I'm listening to you guys over here. So the area is going to be equal to, what do I have to multiply?
4.5 times 8, 4 times 8.
Or the other way around, whatever you want to do. What's 1/2 of 4, you guys?
2.
What's 2 times 8? And I measure in centimeters by centimeters. So it's going to be centimeters squared. Just ignore them. You know what? Dion just asked a good question. How do you know which one's the diagonal 1 and the diagonal 2? It really doesn't matter because with multiplication, we can multiply them in different orders anyhow. You know, I would have gotten the exact same answer if I did 1/2 of 8 times 4. I would have gotten exactly the same answer if I did 1/2 of 20 times 14. Shad. Say it again. That's how I got 16. You can go into your calculator. You know, you can do this multitude of ways. 4 times 2 is 32. What's 1/2 of 32? 16. What's 1/2 of 8? 4. What's 4 times 4? You know, it's just our multiplication is switchable. All right. Moving on. Example, extra practice 3. So find the measure of a central angle of a regular polygon with 8 sides. Well, central angle, we talked about the sum of the measures in a polygon is going to be 360. It's like going around a circle. This has 8 sides. So just taking 360 divided by the number of sides is going to give us what that central angle is. Is it 45 if I remember right?
Yeah.
Okay. So we can say this. 360 divided by n equals the central angle. Why don't we just sort of formalize that little formula out to the side? 360 divided by n equals your central angle. Now, number 4 is just a little bit different setup because they tell us that the central angles are actually 40 degrees. Number 4 is a different setup. They're telling us the central angles are 40 degrees. Well, we'd set this up. I got 360 divided by, they want the n, and I get 40. They want the n, and I get 40. So why don't let's undo divide by n. I got to get this n out of the denominator. I'm going to undo divide by n by multiplying by n. And so actually I'm going to write this now as 360 equals 40 times n. I still have one more step of undoing. Now I'm going to divide by 40. 360 divided by 40. How many sides does this have? Must have been 9.
He's not.
So that's a work backwards problem. Must have been 9 if I got the central angles to be 40. Now this is some of the basics of this section, but now we're going to get into where it takes a turn to being quite a bit more complicated. So what I'm reading here in number 5 is that I have a regular pentagon with a radius of 4 inches and its side length is 3 inches. I do know that, it's right here too, this apothem for a regular pentagon is going to be important. So actually that's the first thing that I'm going to show you how to find. Now we're going to sketch the best we can a pentagon. Take a second and sketch the absolute best you can a pentagon on that page. And then my next move is going to be to put a center on there so I can look at that radius they talked about of being 4. And they also talked about the side lengths of this pentagon being 3. The radius was 4 and the side lengths were 3. This is the information that we're given. Well, so what would the perimeter of this thing be? What would the perimeter of this be? 15, yeah. All the way around the perimeter would be 15. We'll use that later, but that's not what they're talking about right now. Everybody cool with, like, good enough with your... Let's break this down into lightly with your pencil. Let's show those 5 copies of that triangle. Lightly with your pencil, show those 5 copies of that triangle. And the reality is that all of these lengths, these are all radii. They're all 4. I also know that all of these sides are all 3. Well, what's that doing for us in terms of the apothem? Like 20 plus 15. You know, the only thing that really is relevant right now is that the perimeter would be 15. I don't know what adding together these 5 measures would do for us. I want you guys to grab a colored pencil. I want you to highlight one of these triangles. Grab one of your colored pencils and highlight one of your triangles, and then I'm going to actually increase its size and I'm going to bring it over here. So I'm highlighting one and then I'm going to blow it up and I'm just going to bring it over here all by itself. Now, my whole undoing and whatnot there is because we got to find the apothem. Like, you guys are looking at these numbers and it's like, okay, the perimeter is 15, great, but you know, what the heck is the apothem? The apothem is the distance from the center to one of the sides. And so when I draw that in there, it's really little, but that's why I wanted you guys to bring this bigger copy over here, because the apothem is the length of... Well, you're guessing right now because we got a lot more mathematics to get into here. Okay, and I'm hearing Tay say something. The Pythagorean theorem is going to come in handy. For sure. Because we got to find out what this little a is. So let me just put that as a squared. The b would be here. How long is this side? You got it. So you can see there's a lot more going on here than just like adding some numbers up. We're not in middle school anymore. We wouldn't expect that just adding the things together is going to be what we've got to do. And then C would be the 4 squared, exactly, because I had to actually take that triangle that there's 5 copies of and break that in half to figure out what this apothem is. Now, you guys busting your calculators out. This is 2 1/4. 1 1/2 squared is 2.25, and 4 squared is 16. Let me do the math for you. All right, let me do the math for you. Now I'm going to go and take away 2 1/4 from both sides. And I'm going to find out that a squared is 13.75. Let me do the math. Trust me on this. Do the calculations, I should say. And then I'm going to take the square root of both sides. And I'm going to find out that that apothem is about 3.71. It's not the friendliest thing in the world, but we've got it now, and we need it, the apothem. The distance from the center to a side, and it comes down and hits that side at the midpoint. We used that idea when we came over here and we said about having the 1 1/2 as the length of the bottom of this. Now, find the area of the pentagon. Lord, now we got to go and find the area of the pentagon. If I remember right, the area of the pentagon is going to be times A times N times S. I like to use N and S for the perimeter, although you guys already knew that the perimeter was 15. So for this pentagon, the area is going to be equal to 1/2 times, well, let me use parentheses because I'm going to have a decimal here. 1/2 times 3.71 times N. What's the N in this case? Times, what's the S? How long is a side?
3.
Okay. So going into my calculator, I'm going to just drop it in there like that while you guys get caught up on writing stuff down. Where'd I get 5 from? Somebody answer Billy's question.
Say times 3 or equals 3?
Number of sides.
So what should it say? Times 3 or equals 3? N is the number of sides, and that's where the 5 came in. This is 1/2 times the apothem times N times S. Look back at the formula on the previous page. That's where this came from. And I got about 27.825. This was measured all in inches. I'm multiplying inches by inches, and I'm winding up with inches squared. I could not have found the area of this pentagon that they describe without the apothem. And for sure down the road, like there's going to be places where you're given the number of sides and the side length, and you got to know, oh, I got to go in and get that apothem length. Now, last problem here, this is almost, okay, great. I just want to know when I'm starting this in the video, just because my second hour missed the last problem. This is about 13 minutes in. A regular hexagon has an apothem of 10 units. The only thing we have is that the apothem is 10 units. I'm going to go draw a regular hexagon carefully. The only thing we know is the apothem, that's not bad, is 10 units. So really, that's it right there, 10. That's it. That's the only measure we have. That's a right angle mark. It's getting dropped in there. That's the only measure we know. Now, for this particular problem, I want you guys to think about how, and I'm going to grab my colored pencil and just sort of, I'm going to take my colored pencil. How many copies of this triangle are there, you guys? There's 6 of them. Yup. There's 6 copies of this triangle. Now, this would be the radius, and this would be a side length. Yeah. Okay.
You do the apothem, like it'd be 20 from top to bottom, because the apothem goes in the middle, and then you would divide it along 2 sides, and it would be 10 for each of those 2 sides.
Oh boy, you got a good idea going on. The going all the way across the figure to 20 isn't going to help us out a whole heck of a lot. Oh, I wish, Jeremy, nice thinking on your part. This is actually like a special relationship about a triangle, because would you guys be cool with me? What would be this central angle in here? 6 sides, 360 divided by 6. 60. Yeah. This angle all the way across up here would be 60. You know what? This is a regular hexagon is made up of triangles that are 60 degrees at every angle. Every one of these angles is going to come in and be made up of 60 degrees. Every one of them. Yup. And so, and I kind of wrote that lightly on my page because the reality is that I've got to break that off in half. Like I got to go and find out this side length and this radius, but I'm going to have to break it off in half. So that gets a little funny in and of itself.
So it's going to be like 90 altogether. 80.
Well, there is a relationship that goes along with these triangles. This is called, like, the piece that we just broke off is the piece that we're breaking off, and I'm going to go take my other color now and I'm going to highlight half of it. You guys okay with that? Now I'm even breaking this down even further. I wish we could. Yeah, the idea about a Pythagorean theorem isn't a bad one. We know this, and actually we know this. Oops, I lied. We know that that length is 10. This over here is going to be 60. And when we went and split this in half, this angle up here is going to actually be 30. So there's a special relationship about the side lengths of a 30, 60, 90 triangle. There's a special relationship about the side lengths of a 30, 60, 90 triangle. In a 30, 60, 90 triangle, I'm going to draw this over here just to show you if this is 60 and this is 30. This length down here, if we know what this length is, the hypotenuse is twice that length. And that length times the square root of 3 is equal to this side. So it's actually pretty complicated what's going on here. I was working on this and special right triangles with my Algebra 2 kids. And I think there's this assumption in here that this is something you guys have experienced before. That's why I'm like, ooh, I gotta go drop this 30, 60, 90 in here. This isn't gonna be easy. Now, if we wanna find out what this side is, we need to know what little a would be. And as crazy as it sounds, little a is gonna be found by doing, this side is expressed as a times the square root of 3. I just want to know what a is. If a times the square root of 3 is actually 10, how about I divide by the square root of 3 to find out exactly what that a length is down here? It's part of the rule, square root of 3. It's the special 30, 60, 90 relationship. It's part of the rule. And so when I go and divide by 10 divided by the square root of 3, I'm going to find out that this length down here, yeah, Billy got it, about 5.77. Okay. Now, let's double that because that's going to be the length of this side right here, 11.55. So I just found the other missing sides in this triangle. I feel I'm going too quick. You're going to see me kind of work backwards into our drawing now. What is this telling me about what I needed way back here? So this 11.55, let me drag it over here. You guys okay with that? Let me drag it right in here. The bottom's not 5.7. What is the bottom? 11.55. Nope. Nope. I'll have to go back. It's not 11.55. What is it here? This piece is 5.77. Double it. Boom. There you go. When I was answering the phone, you guys got it. So taking 5.77 and multiplying it by 2, I got about 11.54. So the side length is actually 11.54 and the radius was this. Holy cow. Now, oh, really? It's the same? That's right, because this is a 60, 60, 60 triangle. And they're, yeah, you're right, 5.5. Yeah, I'm sorry, I was answering the phone. All of these are 11.55, all of them. Now, area of the hexagon, 1/2 times the apothem times n times the side length. Oy, oy, oy. That's what this is asking for. Last one, area. A half, they told us the apothem was 10. That was the first thing we knew. The n is 6. We just found the side length to be about 11.55. So when I go through and I multiply all these pieces together,
You get 32.
6 sides. The same question you asked me on the last one, sweetie. Where are we at? Measuring in units. They didn't give us a measurement. So when I multiplied that through, that's the n. So this is the apothem, the number of sides, and the side length. 1/2 times the apothem times the number of sides times the side length.
346.
Now, once I...
Your